to turn on the microphone, but all of you are here, so that's not a big issue. But now it's working. Okay, so we just completed the two lines for volumetric strain. For the strain softening part, when it goes through a peak, then it dilates. For strain hardening, it will always continue compacting and losing porosity, even though it goes to shear yield. And when it gets to this point, the final point, it's not going to change volume anymore. And at that point, there is no change in deformation. Okay. Do you have any questions about what we're seeing here? And to me, this is the most important part. It's trying to understand what we're seeing is just a stress path and what is the role of the yield surface. And that is, let me explain again that when you go first through the yield surface to this curved region, and on the right side of the middle, you will go through a process of strain hardening because you are on this side of the curve, and when you have this, you have compaction because you always have a positive component in the direction of compression, while you are on this side. If I had a vector somewhere over here, when you hit this line, you're going to have a dilation because your component of the plastic strain is going to be pointing to the left. Yes, Stephanie?
Is this just for uncemented sediments?
This is for uncemented. If you had a cemented material, your line would not start here, but will go a little bit above this point. And this line will go above this point.
Like
so, exactly. So at the P prime equal to 0, still you can resist some deviatoric stress.
But overall the paths would stay?
The shape will be more or less the same, yes. But this is going to shift a little bit to the left. Same as this line. Here it has an intercept at some distance from 0. It will be the same thing over here. This surface will be a little bit over that point. Okay, so let's try to see, now that we know the basic part, let's try to see a little bit of the math that we need in order to predict these plastic strains. Because at the end of the day, all we want to do is to predict those plastic strains. And the first thing we want to do is to look at this line M, because that's going to be one of the two lines which is going to define this response. And that line M, as you can see, is just a straight line of Q as a function of P prime, and tells you that Q is equal to M times P prime whenever you are at this critical state line. Sure. All right. If this is the case, then let's try to see what are typical values of M. M is going to be equal to Q divided by P prime, and according to definitions of Q and P, Q is sigma 1 minus sigma 3, and P prime is sigma 1 plus sigma 2 plus sigma 3 divided by 3, right? But if you remember, for axisymmetric conditions, sigma 2 is equal to sigma 3. So this is just going to be 2 sigma 3s divided by 3. And so I'm going to further assume here that, let's say that the friction angle is equal to 30 degrees, and if this is at failure or yield, what is going to be the value of sigma 1 compared as a function of sigma 3? If friction angle is equal to 30 degrees, the maximum value of sigma 1 is going to be 3 times sigma 3. So this one is going to be 3 sigma 3s minus 1 sigma 3 is going to be 2 sigma 3. And if this is 3 sigma 3 plus 2 sigma 3s, that is going to be 5 sigma 3s divided by 3. So 5 sigma 3s divided by 3. And that's going to be, if you move this one to the top, that's going to be 6 divided by 5. That's going to be about 1.2. So if the friction angle is about 30 degrees, something similar to what we have been already seeing, m is going to be equal to 0.2. But there is one more thing I have to say here. This is not just a failure angle, as we have seen before in the Coulomb criterion. This is the critical state line friction angle. And it's similar to the friction angle that we have talked about before, but it's in this model is what defines that line. And we know that we can go over that line, the peak value, and sometimes that's going to be the maximum value in this case.
And that's unitless?
This one? M is unitless, yes. And when this is the case, sigma 1 is equal to 3 sigma 3. In general, M is going to be equal to 3 times 1 plus the sine of the critical state friction angle 1 minus sine critical state friction angle minus 1 2 times plus this. And that's going to be the general equation. Okay, so we have the equation of that line. That's going to be the maximum attainable value of Q. Again, if you go on a strain hardening curve, and that's going to be the value it tends to when you go in a strain softening curve. Right there. It's called critical state line because any condition after yield, it will tend to that line. All the state of stresses will eventually land on this line. And after that, it's not going to change anymore, unless you have a different confining stress. Okay, the next thing we have to look at is the yield surface. Let me bring that back. We have the equation of the line. Now we'd like to have the equation of this ellipse. And that's going to be the yield surface is going to depend on Q, is going to depend on P, and it's going to depend on one another parameter, which is something which is called the preconsolidation pressure P naught. Let me write it, and then I'll explain what that is. Okay, so this is just equation of an ellipse. And this is the yield surface. And you can recognize probably this equation of an ellipse because we have a term, one of the variables, which is q, which is squared, and the other variable p prime, which is also squared. When you multiply p prime times p prime, you get p prime squared, and a couple of constants. You can check this equation. For example, when q is equal to 0, what is going to be the value of p prime? What? Let me take a sip of my tea. No. Well, yes and no. There are two solutions. So if q is 0, you can have p prime equal to 0. That's going to be the trivial solution. The non-trivial solution is going to be when p prime is equal to p naught prime. And that's actually this point over here. So when q is equal to 0, you're either here or you're there. And this is the point that we said is called the preconsolidation pressure. And it is very important because it defines what the size of the ellipse is. And it's not a constant, it's a variable. These all are variables. And for example, when q is equal to mp prime, then what is going to be the value of p prime? You can check the equations, okay? But you will see that when that's the case, the value of p prime is going to be the preconsolidation pressure divided by 2, which means that when you are exactly at the critical state line, when this surface meets that point, that's the center of the ellipse, and that's p prime divided by 2. But it's just an equation of an ellipse, and this is what is going to allow us to calculate our plastic strains later on, because the derivative of that is going to tell us the plastic strains. Okay. As I was telling you before, P naught it's a variable, and that's very important. And it's what is going to define the size of the yield surface. And it's also what is going to be our hardening parameter. And we're going to use that because we're going to relate that P naught prime, the preconsolidation pressure, with porosity, or what is the same as a function of the plastic strain in the isotropic component. All what I'm saying here is that preconsolidation pressure, let me add here the name, preconsolidation pressure is linked to porosity, which is something that I hope that you see it's more or less obvious, and is what we were saying before, that porosity depends on compaction. And I hope that you can see now that the size of this ellipse is this is the preconsolidation pressure, but this also depends on porosity. The larger the porosity, the weaker the material is going to be, and the smaller this ellipse is going to be. The higher the preconsolidation pressure, the more compact, the stiffer, and the stronger the material is going to be, and this is going to be larger. So when we go through a path of strain hardening, actually the yield surface is increasing every time. And that's what makes the material get stronger. And let's see that with an example. We're just going to now do the complete path of a strain hardening response. Again, if this is Q, this is P prime. Let's say this is our critical state line. And let's say this is our initial yield surface. Yes. Okay. So let's start somewhere over here, and we'll go through a path of triaxial compression in this direction. Again, in these plots you can do any type of stress path, but here we're just doing triaxial compression, and basically we're going in this direction. The result of this triaxial compression is that when you go over this yield line, and let's say somewhere you stop over there, you have compacted the material and you have gone through a plastic strain after you cross that line. Because you go through a plastic strain, the porosity of the material now is lower and it's irreversible. And that porosity, that loss of porosity is going to make that mud rock to be, as we say, stronger. So the new yield surface, let's say that we go this direction and then we unload it. The new yield surface at this point is going to be a yield surface that is over here. So if P naught prime was over here, after you go through that deformation, it's going to move into that direction. If we take a look at here, the strain in the deviatoric part, this looks something like this. We go through, first is the elastic component. Once we go through the plastic component, then this one starts to curve. If we do an unloading, we're going to assume that we come back on the same curve or the same stiffness in which we had before, and we get there. If we look at the volumetric part component, this is going to be the rock compacts. It gets to the yield point somewhere over here, and it starts compacting more when we will not recover all of that volumetric strain, and we get to a point over here. So getting through the yield surface is going to cause a permanent deformation and a loss of porosity. remember that this volumetric strain is going to be linked to porosity. And once we go through the yield surface, that's going to be irreversible. If we come back and continue loading till we get to the yield surface, now the new yield surface is going to be that one, and this one is going to move from here to there. If you were to unload this material, let's say that you get to here, and then you unload it, it will come back this way, but on the volumetric region, let's say that it tends to a value somewhere over here. You unload it, and it comes back somewhere over here. It doesn't recover the entire strain. So every time you go to the yield surface, you have a permanent deformation in the volumetric strain, and as a consequence of that, the rock gets more compact and also stronger. Yes, Stephanie.
What kind of relationship exists between EQ and volumetric strain? Like, is it linear?
We're going to see that in a bit, and we'll relate that with mostly the porosity or void ratio. But when you get to no change of volumetric strain, you can still have a deviatoric strain. That would mean that your material is shearing, but it's not changing volume.
You also
Or it's getting short in one direction, large in the other, but it's not changing volume.
yeah. Can you also highlight the first on the volumetric strain curve?
Yes.
First curve that you did.
That one?
Okay, so it's there to there, and then the second one goes a little further to the left.
Yes. So let's put names on this. So let's say this is point number 1, point number 2, right? So number 2 will be over here, number 1 will be over here. Number 1 at the end of loading will be somewhere over here. At the end of loading will be somewhere over there, and when it unloads, it will be somewhere over there. Wait. I think this is what it may have caused a little bit of confusion. So the first one returns to that point over here. The second one should return to some point over here. It should be in the same location. But what this means is that even when you unload it, you do not recover almost anything of the volumetric strain. It's more or less at the same point.
Why is that? Why do volumetric strain is hard to recover? Is that because of the grain?
Because it's all goes into plastic deformation. It's a little bit easier to conceptualize this if think about the landslide. In a landslide, you can have one mass, or like a fault. You can have a mass of rock slide with respect to the other one, and the relative volumes or the volumes of the two masses are not going to change volume at all. But there is a displacement that you're not going to ever recover. That's EQ. That's the plastic deviatoric deformation. But you do see a change in, but you do not see a change in the volume. You see a change in this deformation, but you do not see anything in the volumetric part. And again, when you have like this moving relative to another surface and it's not really a change of volume, then that's when you just have a change of deviatoric strain. Okay, the whole idea here is now how to relate. We know now that this value is a constant and depends on compaction. So this value P naught, we need to find an equation that's going to allow us to link it to the plastic strain in isotropic direction, or the isotropic component, and we're going to link this to a function that is going to be a function of porosity, but we'll define another variable which is very useful for this model, which is something called the void ratio. Is any of you familiar with this definition of void ratio? It's just an alternative version of porosity. For example, if let me do it down here. We have a rock filled with grains and with pores. We can conceptualize this as volume of the solids and volume of the pores, right? And here, porosity is just equal to volume of the pore divided total volume, where all of this is the total volume, and void ratio is defined as the volume of the pores divided the volume of the solids. And you can work with these equations taking into account that total volume is volume of the pores plus volume of the solids in order to show that that void ratio is porosity divided 1 minus porosity. It's actually very easy. Let's say that the total volume is equal to 1, then void ratio is equal to the volume of the pores, which is just going to be porosity, and volume of the solids is 1 total volume minus volume of the pores, is the equation that we see over there. So it's just another way of telling what porosity is, but with emphasis on the pore volume respect to the volume of the solid. For example, if you had a void ratio equal to 1, that would mean that there is as much space distributed in pores as it is in the solids. And that will be a porosity of how much? 50%, right? You raised your hand, Stephanie?
Yeah, I think I'm thinking about that a little.
Okay. Okay, well, then let's continue working on this idea. The idea here is going to be that when we have a change in the plastic strain on the isotropic component, if this one is positive, that means that we have a compaction. And if we have a compaction, that would mean that we would like to have, or we would like to model stronger material or an ellipse size which increases. On the other hand, if we have a plastic strain on the isotropic component, which is negative, that would mean an increase of porosity. And if we have an increase of porosity, we would like to have a weaker material. Okay, and in order to do that, we're going to define, or we're going to use one more line or one more function that is going to allow us to do this. And that's going to be the compaction curve. Let me try to think a little bit here if I change this how I was doing it before. Probably it will make a little bit more sense. Yeah, let me change the way I did it last year. We're going to go, based on this idea, we're going to see how a compaction curve is going to be useful for us. A compaction curve is basically a curve that tells us what is porosity as a function of stress. And for this particular case, let's say that we're talking about vertical stress, because that's the most typical example that you do in the laboratory, and that is also applicable to the field. As you increase the vertical stress, compaction or porosity is going to decrease, right? And in the laboratory, we usually do this under this, by now, very popular 1D strain condition, in which we load sediments in between two sort of end caps or platens that move parallel to this axis, let's say the vertical axis. Here we apply stress, and if this is a brine saturated rock, what do you think we should do in order to make that rock compact? If it's brine saturated and we compact it, at some point we're going to start compressing the fluid inside the pores. So what we have to do is we have to make some holes over here, and usually here you put some sort of drains, usually made of stainless steel, that will allow the fluid to come out, so we don't have any undrained loading. Because at some point you will start to compact the pore space, and you don't want that to play any role into the compaction. And the basic idea here is that as you increase the vertical stress, porosity is going to decrease. Now, how it decreases, that's what is going to be important for us. Do you think this is going to be a linear function or a non-linear function? Is it going to be concave or is it going to be convex? Let's assume these are like linear axes. So let's let's think about a mud, mostly made out of clay, maybe some silt particles, at very small stress, effective stress. You're going to have, let's say, high porosity. For very loose muds, if you change a little bit the effective stress, when they are very loose, you would expect a large change of porosity. And when they have a significant stress on them, even if you have this a relatively large change of stress, the porosity is going to change very little. So the response is going to be non-linear.
How do you measure porosity in this case?
In these cases, what you do is you measure what is the displacement as you compact them. And since you know what is the initial amount of rock at the beginning, and you know what is the initial porosity, by knowing how much it deformed, you can tell what the porosity is.
Can you measure the volume of water also?
You can also measure the volume of water. Usually that will be a less accurate measurement of volume, but you can also do that, yes. Okay, so I don't have any hard evidence here to show how this behavior is going to be, but just imagine that at the beginning it's very easy to compact a rock, but as it gets more and more compact, the grains get closer and closer to each other, and every time it's more and more difficult. And that's why this curve is non-linear. And here we're talking about big changes. We're not talking about 1% change in porosity. We're talking about 10%, 20%, 50%. So we're talking about large changes of porosity, irreversible deformation, and plastic deformation. So all of this path is going to be a path of irreversible plastic deformation in a process of compaction. Sometimes when we do this kind of test, we also do some unloading. So let's say this is the loading curve. You could also do an unloading path, but you will see that unloading doesn't follow the same path as loading, because unloading is mostly elastic, while loading is inelastic. And because of that, these two curves are going to be different. Let me put this in an easier plot. And instead of plotting here sigma v, I'm going to plot the natural logarithm of sigma v, where this is porosity. When you do that, porosity data, most porosity data will tend to fall in a compaction line, just in a single line. And it's going to be straight line when you consider this a natural logarithm. And the unloading part is going to be also, there are going to be also straight lines. So this is going to be loading, this is going to be unloading.
Porosity is on a linear scale?
Porosity is in linear scale, and this one is stress is in a logarithmic scale. And the equation for that is, as you may expect, you have it in your in your homework sheet is going to be blah, blah, blah. Is it going to be the one with void ratio? Void ratio is equal to initial void ratio minus CC natural logarithm of sigma v divided 1 MPa, because you have to make that dimensionless. And remember that void ratio is just similar to porosity. All right, so here this CC line, I think there is a minor mistake here. Okay, it doesn't matter. Yeah, I think my notes are correct here. CC is going to be used for the unloading part, which is the elastic part, and that's going to be, let's see where I can draw this, probably here. It's going to be this. If this is equal to 1, CC is going to correspond to the slope of that unloading curve. But notice that in the loading region, if this is equal to 1, this is another one which is called CS, which corresponds to the plastic part, and in that one it's the same equation but with CS.
What is left by 1 MPa?
Because you cannot take the logarithm of a quantity with a unit. You need to make it unitless. Otherwise, that's ill-defined. All right, so let's try now to use this with what we have already seen. So we know that our materials are non-linear because porosity and deformation depends on the logarithm of stress, and we know that we can go through loading and we can go through unloading and loading again, but the one that is on the plastic part is the loading curve. So for example, let's see if I can put these two plots together. Okay, yeah, I think I can. Let's say that I start somewhere over here, and let's say that's a point right over there. Oh no, actually it's right in here because I'm in the elastic region. If I load it and I get to that, that's all elastic until I get to the yield surface. So that's going to be up to there. Once I go into the plastic part, I hope onto this line, the plastic line. And let's say that I lose all of that porosity and I get to this point. And if I unload at that point, I get back to here, unloading. If I load again, now the new point at which I'm going to have a plastic strain is not going to be this surface anymore, but it's going to be that one. So when I come back this way, and only once I get to the yield surface, I jump again onto the plastic deformation line, and I go up to there. So this is the link that we need in order to relate now the increase of the yield surface with the compaction line. And for example, with the the project that we want to work with, I like that you digitize this data, which is real data from a place in the Gulf of Mexico, which is offshore. And what you see over here is track number 1, gamma ray, which tells you what? What does gamma ray tell you? And in general, what, like shale or clays? Usually clays, they have more radioactive minerals. So the more clay you have, the more shale you have, the larger the gamma ray is going to be. And you can convert that into a percent of sand or percent of clay. So what this means is that in this plot you have about 10, 20, 30, 40, about 40% sand up to this point. Well, let's say up to this point, but at around this depth, your percentage of sand gets a lot less, 30, 20%. At this point, similar to what Dr. Milliken was showing today, if this is your sand, it becomes disconnected. The sands, they do not see the other sand, but they are just mostly surrounded in a clay of matrix, in a matrix of clay. And it is at this point where you start to have an anomalous compaction curve. Why would you have an anomalous compaction curve? Why would the porosity, you see that it makes sense that as you go deeper, stresses increase and compaction decreases. But you get to this point and porosity doesn't decrease anymore. What could be the reason for that?
Grain-to-grain contact synthesis or else to go.
Well, but you know, it appears to me, at least from this data, that there is very little sand, so it's mostly sand immersed in a matrix of clay. Pore pressure, so Jack, you were saying? Overpressure, and what means? What? It will resist, and why would overpressure generate?
Because it's shell, the fluid will retain in the first phase.
The rate at which fluids move out is slower than.
Right, so it will be basically up to this point, this is under undrained loading, the water cannot escape, and because the water cannot escape, actually the effective stress is not increasing with depth. The vertical stress increases, but the effective stress does not. So if we were to make a plot of here vertical stress, that one is going to increase, always increases. If we were to make a plot of pore pressure up to this point, it looks like it is pore pressure also will increase, but it will increase less than the vertical stress. That's why effective stress is increasing. If effective stress is increasing, porosity should be decreasing. But as you get to this point, the effective stress doesn't seem to decrease anymore. Even it appears to increase a little bit. So what that means is that if effective stress is not increasing and is decreasing, it means that, for example, at this point, effective stress probably is something like here, over there. And if this is the effective stress, then we have no other option that to, in this case, to assume that pore pressure, it might actually look something like this, where this is the pore pressure and this is the vertical stress, total vertical stress. So what I want you to do in this project is digitize the data with the normal compaction trend or with the data up to this depth. You fit these lines. These are two possible models for porosity or void ratio as a function of effective vertical stress, assuming that up to here is hydrostatic. And after that, using this porosity, you predict what the vertical effective stress is, because it is in your equation. So if this one is known, because it is measured over here, then you can tell what sigma v is. And if you know what sigma v is, and you know what SV is, then pore pressure is just going to be equal to SV minus sigma v. And this is the workflow that is used for calculating overpressure in this type of shales in which compaction is the main phenomenon or the main cause for loss of porosity. And it's something that it's used quite a bit in, for example, the Gulf of Mexico, North Sea, but it's not a solution all the times. For example, for unconventionals, many of these models do not work very well. As Dr. Milliken was showing today, there are some shales in which you have a lot of othigenic cement, and in that case, this model doesn't work very well either. But in most shales, which are controlled by compaction, you can apply this logic and get to calculate what is the overpressure based on anomalous readings of porosity as a function of depth. We will always expect porosity to decrease with depth, but sometimes it doesn't. And one of the reasons is overpressure and undrained loading. So basically, that's everything about the first part. Let me see if I forget anything. No, calculate pore pressure. No, I think that's it. And for that, you need these curves. Okay. Let's see what we're doing with time. I think we can leave some of this for Wednesday, but I like to finish this compaction curve, how to put it together with this. Okay. All right, so this plot of porosity or void ratio as a function of effective vertical stress, we can also do the same instead for a type of experiment like this with one-dimensional strain. We can also do it in isotropic conditions, which mean all stresses increase in all directions the same. And in that case, let me keep that for a moment. It's the same, but I'm just going to write it directly in terms of a void ratio. And instead of sigma v, I'm going to use p prime. And the idea is the same. The higher the mean effective stress, the lower the porosity is going to be, And this is also going to be a curve which looks something like this. And it is exactly the same thing. All right? Okay. So now that we have that, and now we have an axis in common with this curve, let me put all of this together into one plot. Okay, so we know this one, Q as a function of P prime, and we know that this is going to be, here there is going to be a line, which is going to be the critical state line. All right, now what I'm going to do is I'm going to add the void ratio axis as a third dimension over here. Okay. When I add this third dimension in here, these surfaces turn out to be actually slices of a three-dimensional surface, which looks more or less like this. As we said, high porosity or high void ratio, that means low effective confining stress. Low void ratio or porosity, that means high confining mean stress. And this is a line that projects, this is in a three-dimensional space, but if I were to put now this curve into this plane E P prime, it's going to look something like this, and this is called the isotropic consolidation line. And this line is going to be the line in which I have the center of the ellipse at any given porosity or void ratio. So if you look in the from infinity in direction of the void ratio, this is what you see. But actually, this is a three-dimensional surface that combines Q, P prime, and the void ratio.
Can you write down those curves what it look like?
This is a yield surface. On the what is called the wet side. And what do you want me to add? This one? This one is what is called the isotropic consolidation line.
And the very first line you drew in void and Q space, what's that?
This is the critical state line.
No, the one just below.
So this one is on the PQ space.
Yeah, but on Q void space. That first, the top solid line.
The upper limit of the yield surfaces.
I guess that's, yeah.
Which one?
Up. Go up.
This one?
Yes.
Okay, well, this one is on the Q P prime
Oh.
plane,
Oh.
CSL. ICL, it's on P prime E plane. And this one, it's a 3D line, which is not in any plane.
The top one?
This one. I'm gonna make it in color.
Yeah.
That one.
In 3D space.
Yeah.
So that's going from high void ratio
Correct. It goes from high boil ratio to low boil ratio, and it also goes from small mean stress to high mean stress. And it also goes from low Q to high Q. So this one is in it's not in any plane, it's in 3D.
Yeah.
And what we see over here are just sections of that. And what that means is that, for example, when we move from here to there, that means that we're actually moving in this direction. So if I go, let's say, from here to there, that's a compaction stress path, and we get into yield surfaces which are larger and larger every time. And that's where we get this phenomenon of strain hardening. There is just one little thing that I like to highlight, is that it is easier to work with these surfaces, and we'll do the same in our equations with this isotropic consolidation line. But remember that that isotropic consolidation line is not the same as this 1D strain line. And the stress path of compaction in the isotropic consolidation line is not the same as the stress path that goes into 1D strain. And that's very clear when it's kind of difficult to make it in 3D, but 2D is a little bit easier. This is Q, this is P prime, and this is void ratio. We have our critical strain line somewhere over here. We have our yield surface, let's say somewhere over there, and an isotropic consolidation line, let's say if it's this one, we can go through a process of compaction that goes, let me change this a little bit to make it more obvious and to fit on my plot. Let's say the yield surface is here. No, that's terrible ellipse. Give me one more chance. Okay, so if you go through a process of compaction, and let's say you start right here, when you go to the isotropic consolidation line, you go this path, and it will be a path that goes from here to there. However, we don't see that very often in real applications, and the most common application that we saw is the 1D strain path, and that would be a path that goes somewhere over here. It's not this isotropic consolidation line. That's going to be another line which it is more or less parallel to that line, and in this case you go this way. So it's not exactly the same thing, but it is similar. And again, an isotropic stress path involves change of strain, which is the same in all directions. And a 1D strain path is just has strain in one direction. And in the other two, one of them that we cannot see, they are zero. Just to complete the picture here, most common sedimentation, natural compaction, and also with depletion. And because this is the most common one, that's the one that we're going to be interested in, and we're going to make it a little bit more difficult in solving that in the project to do a triaxial case as we go through the yield surface. And I think with this, we're good till Wednesday. Basically, we'll see the equations that allow us to predict those plastic deformations. You have a question, Jack?
Yeah, I'm having a hard time to picture the line on P prime and Q space from 3-dimensional to 2D, because it seems like in 3D is only a curve, but in a 2D it's more like a half circle. Do you think?
Okay, so I only drew half circle because there are small variations of that theory that may go into different directions. So let's look in 3D to that surface. Okay, so this is a surface we have been seeing, but I'd like to look at that in 3D. Well, it looks something like this, where this is the cap, this is the elliptical part, and this is the other part on the left of the diagram. But this is not the one I wanted to show. Oh, no, I think I know that one. Okay, so this is another one, another good one. Okay, this is a good one. So in here, for example, this is a little bit, it's in the other direction, but we have the void ratio. Here we have deviatoric stress, and here we have mean stress. Here we have the isotropic consolidation line. Here we have this line in 3D, which is actually the true critical state line. The other one is just a projection of the critical state line. And here we have the elliptical part. And some models, they assume that from here to there, and here we have also a tension cutoff, it goes straight. But previously we assumed that it was elliptical, but that depends on the model that you apply. Some of those go like just straight, some of others they go a little bit curved. But it's a surface in 3 dimensions. You were saying something, Stephanie? Yeah.
On an unrelated note, is there going to be a place online to upload our abstracts that you wanted to, or Wednesday? Wednesday?
Yes, I'm going to do that. I thought I did it. Apparently I didn't.
I checked this morning, but
Okay.
you've done it.
No, I haven't done it yet, but I thought I had done it. Okay, I'll do it. I'll do it now.
Is it today or
And I have to check.
today?
I have to check. But I'll do that, okay? All right. Thank you, guys.